is Matt.
Good afternoon, everyone. My name is Matthew Catalano. I'm a rising senior at Boston College. I'm currently working in a collaboration between the Birch Lab, the Van Opinen Lab, and the Gao Lab. We're creating graphene field effect transistor biosensors. My work this summer has been in automating them. So for a brief outline, first I'm going to introduce you to current clinical diagnostics and some of their problems. And I'm also going to introduce you to our biosensing work, how it works, some solutions that it solves with current clinical diagnostics, and also some of the flaws of biosensing. Next, I'm going to tell you about the advantages of automating biosensing and the problems that it will solve. And that's pretty much most of what I've been doing my summer. So that's where most of my talk will be. And then I'll talk about some of the next steps we're taking to improve it further. Oh, that's the robot right there. Some next steps we're going to take to go further, and I'll conclude with a brief summary. So right off the bat, let's say you're a doctor and we have a patient. From symptoms, we expect that he may have a certain bacterial infection, and we send a sample out to a lab somewhere and do a PCR test for the bacterial DNA. They use special enzymes. They use special enzymes and heat cycling in order to amplify the DNA, and then they search for it. This process, however, has many steps and requires a lot of skilled labor, and that means money. And that drives up the cost for the patient. It's also done out of house, and I figure out of house is probably the single most important thing that drives up the cost. More people involved means higher price. However, the biosensing that we do is with a device called a graphene field effect transistor. And this is cheaper because it's more convenient for people to use because of minimal sample processing, and it's cheaper to run a test. It's also sensitive enough to detect a single bacterium. So, excuse me. It works by generating an electrical signal whenever a molecule or body of interest comes in close contact that is charged. We have linking enzymes right here that have a pyrene group that attach to the graphene using pi bond interactions. Those are the same interactions that actually holds layers of graphene together in graphite. This end of the molecule attaches to a peptide that specifically binds to a certain molecule of interest, or in this case a cell. And the close proximity of this charged cell to this graphene device will output a signal that we can detect. Now, this is some data we have from our detection. I'll just back up a bit so I can see it. These right here are the enzymes that we use. I showed you previously in the earlier slide. This one first here is a control that actually doesn't bind anything. These two are the actual enzymes, but they bind a certain bacteria of interest, and that's Staph aureus. And this is the same protocol. And in this one, we have a control. It's not going to bind anything, so we have 0 Dirac shift. A Dirac shift is a value that is unique to a certain material in our transistors. So if you if you put a bed of charge on graphene, for example, the Dirac voltage is going to shift a bit. So if it shifts significantly, you know that you have an attachment. In this case, there's no attachment. As you can see, it's a control. In this case, these two proteins are correct, but we're searching for the wrong bacteria. This is E. coli, this is B. cellus. This one, however, is the correct probe and the correct bacterium, so we have a shift. However, some problems is that they're very small, delicate devices, and shaky hands will definitely ruin them and ruin your day. It's a lot like a high-stakes game of operation. Yeah. We could use more devices on them. This one only has 6. And we needed to measure them one by one, so that takes a long time. And multiplexing is also a little problematic. So as you can see, this bed right here, this is PDMS. It's an inert rubber that we use to sort of like make almost like holes in it and put solution in each hole. And each well is actually its own independent experiment. So if you have, say, multiple biomarkers for the same disease, or you want to screen for multiple diseases at once, you can independently run one experiment and another experiment down there. We would like to increase the number of wells to increase our multiplexing capabilities. But the problem with that is after you get too many wells, sure, you can maybe manage 2 experiments on one device with this, but can you manage 4? Can you manage 8? It quickly becomes more and more complex. So automating it will help solve that problem. This is the Tech and Freedom Evo. This is the liquid handler from the Van Opijnen lab that I am using to automate it. And it's very, very precise. It can get, I believe, a 1/10 of a millimeter above the surface of the device consistently. And that's about the diameter of human hair. So we want more devices and wells. That increases complexity, but that's no problem for the robot. It's precise enough to fit in these small wells. As you can see, more wells on the same surface area. We need to make the wells smaller. And it'll allow us to do more powerful multiplexing because it can handle all the complex experiments for us, because it's much easier to plan something out on paper than it is to actually do it in front of you. And in general, less labor, less error. So I started out upgrading some of our equipment. This right here is a housing that houses the wires that go underneath the device. This right here is a chip holder. The chip goes in there. It's about a centimeter, not cubic centimeter, a square centimeter. The chip goes in there, and it gets pressed down into these holes. There are contacts underneath the holes, and that's where all the wiring goes underneath the box. We have some new lab code that allows for simultaneous device collection, so we no longer need to measure device by device. We can do it all at once, which is nice because all of a sudden, instead of doing 1, 2, 3, 4, 5, 6 tests, we can use one of our new chips that has more devices on it and just scan all these devices at once. As you can see, we've already increased the number of devices. And that's the new chip design with 4 wells, 1, 2, 3, 4, and 8 devices. 1, 2, 3, 4, 5, 6, 7, 8. All right, so next let's start working with the robot, which is very fun. I don't want to break it down. So we have a modifiable script, and it handles complex jobs for us. This is a brief segment of that. You can see it's instructing the pipetting machine to mix solution in the wells, to take it out, then dispense it somewhere else, mix again. Then we move the liquid handling arm, wait for a timer, etc. Everything we once did in front of a chip, we can now just plan out on a piece of software and have it do it for us. And I calibrated the pipette to fit perfectly within the wells, hovering over the surface of the device, and it goes in there perfectly, consistently every time, no wiggling. Now the next problem we have is communication. The data collection equipment we use, right here is what it looks like. It runs on LabVIEW software. And the robot has its own software called Tech and EvoWare. Now, I need to find a way to make these two communicate. And different software requires a sort of translation. I did this by monitoring file changes in a shared folder. Both of them have access to the folder. And if the Freedom Evo completes its pipetting, say it pipettes the solution of interest into our biosensor, it will then change a data file in the folder, which this will pick up, and then this will begin running its test. And this is an animation of the robot doing its magic. As you can see, it picks up a tip, picks up solution from there, and puts it onto the well in there. There's still some stuff we can do in the future. Right now, the automation isn't perfect. There's a lot of improvement that can go through it. The important parts are done. It will manage pipetting for us, meaning it can handle complex jobs. We can increase the number of wells. But in order to have completely seamless automation, we need to have the automation measuring take place inside the robot itself. I would like to get started multiplexing. Now that we have 4 wells on a device, we can do 4 independent experiments in the same chip. And I'd also like to maximize the number of wells on a chip. Right now we have right now we have 4. Who's to say we can't do 8, 16? But in order to do that, I showed you the PDMS polymer before. We need a better well, because we rip PDMS out of a mold, and if we have wells too small, then the rubber's too delicate and it'll tear coming out of the mold. In conclusion, current clinical diagnostics are expensive. They're done out of house and they're inconvenient for doctors, so you ship them out to a lab somewhere and then they do the work for you, and it's expensive for the patient. Our biosensing devices, however, require a lot less skilled labor and a lot less time. Manual biosensing takes time and risks device destruction. You easily touch the surface of the device, ruining your entire day. But with this automation, that's not a problem anymore. And improves biosensing a lot in many different ways. I'd like to thank Professor Birch, my PI, for giving me this opportunity. I'd also like to thank Professor Van Opainen for letting me use his robot and risking me breaking it. I'd like to thank Professor Gao and Wenjian in the chemistry department for synthesizing our peptides for us. Without those peptides, this wouldn't be possible. All the specificity comes from them. I'd like to thank my mentors, I should say, Narendra and Wansei, both from different departments. I need both of them. And I'd like to thank all of you from the RU program and Boston College, and also the National Science Foundation for funding. Thank you very much. Do you have any questions? Tiffany?
Yeah. So for it to complete like a cycle of the padding, how long would it take? How long would the robot take?
I haven't timed it yet,
Okay.
but much faster. Including a test or just the pipetting itself?
Just the padding.
Just the pipetting itself. Right now, it'll take a lot longer than I would like, mainly because I set the mixing speed to be very slow, just to be sure. And I haven't yet started to bump it up, but once I bump it up to as fast as I can get it without damaging or ruining the experiments. I can't give you a number, but I'd say maybe 2 minutes.
Oh.
I just gave you a number.
Okay.
Any other questions?
Are the devices reusable?
A little bit. You can maybe if you wash them, but not really. I've tried, and a lot of times that just winds up with you sinking a lot of time into an experiment, and then realizing that your device failed halfway through, and you wasted a couple hours of your day. I've done that a couple times. Definitely not new ones if you want to have an important experiment. Anyone else?